Hi, in this video we will see what is Deutsch and Deutsch-Joja algorithm, and then we will see how to implement it using classic Python SDK. So first thing is that what is this Deutsch algorithm? So Deutsch algorithm is one of first quantum computing related algorithms that demonstrated that certain type of problems can be solved much faster in quantum computer as compared to classical computer. And its purpose is to detect if a given function is balanced or constant, provided that we are given that function is either balanced or constant. Now let's see what are constant and balanced function to understand it. So consider a function which is a boolean function and denoted by equals fx, and it accepts n bit input and gives single bit output which is either 0 or 1. Now, depending on what output we receive, we have three possible scenarios. So the first scenario is that for all available inputs, if number of output, if number of zeros and ones in output is equal, then that will be the balance function. So consider this case. If we pass 0 to the function, then it gives 0, and if we pass 1 to the function, it gives us 1. Similarly, suppose there is another function where we pass 0, and for 0 it gives 1, and for 1 it gives 0. So these two functions, we can say that these are balanced. And similarly, for n bit, we take n equals 3, then we can see that for first 4 we are getting 0, and for last 4 we are getting 1, means number of zeros and ones in output is balanced, so it is balanced function. And it's not necessary that 0 and 1 should be in order. Like this one, we can see that first 3 are 0, then 4 are 1, and then last one is 0. But if we see overall, then we can see that number of zeros and ones are equal. That's why it's a balanced function. Now another scenario might be that either all outputs are 0 or all outputs are 1. That will be the constant function. So consider this function. In this function we pass 0, then output is 0. If we pass 1 as argument, then output again is 0. Similarly, there is another function. Here we are passing 0, then it gives a 1, and for 1 also it gives 1. So in both these examples we can see that output is constant. Either it is stuck at 0 or it's always 1. Same thing for multi-qubit or 3-qubit. We can see for all available inputs, we can see always output is 0. In this another example, we can see for all available inputs, output is always 1. So these two are example of constant function. Now there might be the one more case where function is neither constant nor balanced. So this is that case. We can see that in this example we can see that output is always 1, but for these two cases it's 0. So clearly it's not constant, but it's not balanced also, because number of zeros and ones are not equal in the output. So in Deutsch algorithm and Deutsch and Deutsch-Joja algorithm, in both algorithm, we do not consider these type of functions which are neither constant nor balanced. Initially we take assumption that the function which we are given, it's either constant or balanced. So that is one of important given thing or promise which we take at the start of algorithm. And one more important thing is that if we analyze 1 bit, we can see that in 1 bit input, function will be always constant or balanced, because we all available input combinations are here, and we can see that there is no case possible where function will not be balanced and not be constant. It will be either balanced or constant for 1 bit input. And for multi-qubit inputs, it might be balanced, it might be constant, and it might be neither balanced nor constant, but we will not consider this criteria, the third one. So this is what constant and balanced function are. So now we know what are constant and balanced function, but now question arises, why we need this Deutsch and Deutsch-Joja algorithm, how it's superior than classical approach. So first let's take example of 1 qubit. So in 1 qubit example, we saw that to detect if a given function is balanced or constant, we need to test the function 2 times. For this case, we can see that we need to test with 0 and then with 1. Similar for all other cases, we need to test with 0 and 1. And only after testing with both 0 and 1, we can detect if function is constant or balanced function. But in quantum approach, using Deutsch algorithm, it promises to solve this problem in a single shot. Means we do not need to pass input to the function 2 times. In single shot, it will determine if function is constant or balanced. How it works, we will see. But now let's see what Deutsch-Jozsa algorithm promises. So Deutsch algorithm is for single qubit, and it can be further extended for multiple qubit, and then it is known as Deutsch-Jozsa algorithm. So in Deutsch-Jozsa algorithm, it promises for multi-qubit also, it promises that it will detect that given function is constant or balanced in a single shot. But if we see classically, in classical way, we need at least 2 power n minus 1 plus 1 times. How? If we see, so it's 3 bit input, means 2 power n minus 1 will become 5 times. So I will just highlight first 5 inputs. So here, for these first 5 inputs, if we observe both 0 and 1, then function is balanced. But for first 5 inputs, if we observe always 0 or always 1, then function is constant. So this is how we do in classical way. How we do it in quantum way, we will see after seeing the Deutsch algorithm. So let's see first proper definition of Deutsch and Deutsch-Jozsa algorithm. So it says that if given function is either constant or balanced, then Deutsch algorithm can predict the nature of function in a single shot for 1 bit input, and Deutsch algorithm can be further extended for n qubit input and known as Deutsch-Jozsa algorithm. Okay, so now let's see how to create the circuit of Deutsch algorithm, and then we will see how its mathematical calculation also. So Deutsch algorithm. Here we take 2 bit input Q0 and Q1 such that Q0 is in plus state here, and Q1 is in minus state at this point, and then we pass both plus and minus state to the arithmetic oracle. Inside this oracle, our function f of x is implemented, and then after taking output from arithmetic oracle, we do not need this q1 anymore, so we just ignore it, and then this q0, we pass this q0 to the Hadamard gate and measure it, and after measurement, if we receive 0 as output, then we declare that function is constant function, and if 1 is output, then we declare f of x is a balanced function. Now at this point, you might see the circuit is simple, but it looks like magic that how it's able to detect if function is 0, if output is 0 means function is constant, and for 1 function is balanced. So for that, we need to go through the mathematics to understand what is happening here. So at step 1, we saw that we are taking q0 and q1, and we are passing q0 to Hadamard, means it will become plus 1, and then we are passing q1 to the NOT gate and then Hadamard gate, so it will become minus, and then we are writing like this. Now we can rewrite it like this again. We can expand the plus state, which will become 0 state plus 1 state upon under root 2, and then multiplied by the means tensor product of minus, and then we can take this minus inside and then write with 0 and 1 like this. And after that, in this second step, we pass it through the oracle, and this is here real magic happens. So after passing through the oracle, we can write it like this. So this is basically same expression, just we had written u of f, and then we use the formula of phase kickback. So in phase kickback, we know that if we pass state x or psi with state minus to the oracle, then we see the phase kickback effect, means the phase of this minus gets kicked back to the original state, means x state, and if this -1 will be multiplied with this x or not, it depends on the function which is implemented inside the oracle. So I will just we discuss this thing in detail in phase kickback video, but I will just quickly show again. So in phase kickback effect, what happens that if we take q0 and q1 such that q0 is control and q1 is target, and if we have q0 as +1 state and q1 as minus state, then it is expected that control will affect the target, but instead target comes out as it is, like this -1 came out as it is, but controls get affected because of the phase of target. So because here we have minus, this plus will become also minus. And we also saw how this we can derive this formula. This one we are using same formula which we derived in phase oracles. So input is x and minus, and after passing through this oracle u of f, we see that we got the phase of second qubit in the first qubit, or in other words, we got phase of the target in the control. So using phase oracle, we can using the concept of phase oracle, we can rewrite this psi2 as this. So we see this uf got inside this bracket, and it affected both our first and second term. So this is the first term, second term, and with first term we have this -1 because of phase kickback. Now similarly here again we have -1 because of phase kickback. And here we see that the function which is on top of as a power of -1, here it's 0 and here it's 1. Now this is the same diagram from above. So we are at this point now. We have psi2, but now we know that we don't need this q1 anymore, which was in minus state. The only purpose of this q1 was to create the phase kickback effect inside oracle, and that is done now. So we can take out this minus from this and this and ignore it. So here I had just ignored or removed that minus state, and at this point we are at this psi3, and this is basically same expression from psi2, means this one, only minus is removed. After that we will apply Hadamard gate, but let's see two different cases. What will happen if function is constant, and what will happen if function is balanced. So suppose function is constant, and if function is constant, we know that either both are 0 and or both are 1. So f0 equals f of 1. Now let's suppose the first case when both f0 and f1 are 0. So if both f0 and f1 are 0, means this term and this term will become 1, and we will receive this one 0 plus 1 upon under root 2, which is equal to plus state. Another case we know for constant function is that both 0 and f of 0 and f of 1 are 1. So if both f of 0 and f of 1 are 1, then both this term and this term will become equals to -1, and we can take out -1 upon under root 2 like this, and rewrite it like minus of plus state. So this is the point, we have plus state at this point if function is constant, and we know that if we pass plus state to the Hadamard gate, it collapses to 0 state, and that's why here we had written that if we get 0 at the output, means function is constant function. Now let's take another case when function is balanced function. So if function is balanced function, means output have both 0 and 1, means outputs are not equal for f of 0 and f of 1. So first case, let's take if f of 0 is 0 and f of 1 is equals to 1. So putting values here, we will get 1 for this term because this is f of 0 is 0 here, and minus 1 for this term because f of 1 is 1 here, and it will become minus 1. So we will get this expression which is equivalent to minus state. Similarly, if we see for f of 0 equals 1 and f of 1 equals to 0, we get minus of minus state. And so for balanced function at this point, we have minus state, and after passing minus state to the Hadamard, we know that we receive 1. So that's why we had written here that if output is 1, means function is balanced function. So this is what is the mathematics behind how this Deutsch algorithm is working. Now let's go ahead and implement it using classic SDK. So I will go to the Jupyter notebook, and this is same thing which we had discussed till now. I will just head over to the implementation part, and let's quickly review the code. So in the code, first I am importing the from classic library. I am importing the necessary modules for creation of circuit, and then I am importing these two built-in functions. First is Hadamard transform, and second is arithmetic oracle. Now I am importing Hadamard transform to implement this and this Hadamard here, and I am importing arithmetic oracle for this part from here to here. So one important thing regarding this arithmetic oracle built-in function is that by default it implements this q1 as minus 1 for the q1 as minus state for the purpose of phase kickback effect. So this thing, if we use this arithmetic oracle built-in function, then we do not need to take care of q1, we just need to take care of q0. Now we define our number of qubits as 1, and this is our expression which is f of x, and here we have written that f of x equals x less than 1. Now if we see, we have 1 bit input, and our expression is f of x equals x less than 1. So if input is 0, then f of x will be true, but if one input is 1, then f of x equals false. So we can see that in output of f of x, outputs are balanced, means one output is true which is equals to 1, and one output is false which is equals to 0. So we have both 1 and 0 in the output, means function is balanced, and according to our discussion we should get 1 in the output, because for balanced function we receive 1 as the output of Deutsch algorithm. So till now we define number of qubits and our expression. Now we apply Hadamard gate to our q0 to make it to the plus state at this point, and then we pass our x to the arithmetic oracle. We are not taking care of q1 because this is already done. It's already part of arithmetic oracle function, and then once we have the q0 output from arithmetic oracle, we again apply Hadamard gate to it, means this step, and then we measure it, and then we synthesize the circuit, and this code is to execute, and this code will check if output was 0 or 1. So I will run it. Let's see what we get in the output. Yeah, so we got output as 1, means the function is balanced function. Now till now we had seen multiple times, we have seen the circuit multiple times, but let's see once again in the classic platform and analyze it. So here is our circuit, and we can see that in q0 we are applying the Hadamard gate, and this is arithmetic oracle, this is auxiliary qubit, and if I expand arithmetic oracle, then we can see that in auxiliary qubit we are applying NOT gate and Hadamard gate, which will make it into minus state, and then we are passing plus state and minus state to the oracle, and after oracle here we are measuring the Hadamard gate, here we are passing our q0 to the Hadamard gate and then measuring it inside oracle. Let's see what we have. So Again, we see the same circuit which we discussed in Oracle video. We are applying subtractor, and again we are applying subtractor, and here we are taking the XOR operation. If you are not sure why we are doing this, I would recommend you to check back Oracle's notebook, and then you will understand why we are doing like this. But for now, let's execute the circuit. And we had already seen the output in uh, Jupyter Notebook, but here also let's see. So when we run in IDE, we can see that if we hover over this bar graph, we can see that output is 1 here, and it shows the number of times this algorithm is run. So if output is 1, means function is balanced. Now let's make this function as constant. So I will make expression as x less than 13. We know that both 0 and 1 are less than 13, means output will always be true, and if output is always true, means it's constant function. So for constant function, we will receive 0 in the output of Deutsch algorithm, and that's how we know that it's constant function. Let's see the output. Yeah, so in output we got 0, so clearly it's constant function. Now we are done with Deutsch algorithm. Let's move on to Deutsch-Jozsa algorithm. So at starting only we saw that Deutsch-Jozsa algorithm deals with same thing to detect the nature of function, but Deutsch-Jozsa algorithm is for multiple qubit input. So in Deutsch algorithm we were taking 1 bit input, means either 0 or 1, but here we are taking multiple bit input, means it could be 0 0 0 or 1 1 1 or anything, means n number of bits can be there in the input. And this is q1, which is in minus state. So we make all our input n bits in plus state, and this Hadamard in this q1 in minus state, and then we pass it to the Oracle. And after passing through Oracle, similar to last time, we ignore this q1 which was in minus state, and to our n bit inputs we apply Hadamard gate, and then we measure it. And after measurement, if all bits are 0, then it's constant function, and if even a single bit is not 0 in the output, that means it is a balanced function. So let's see this example here. For n equals to 3, means if n is 3, means we have 8 different output available. So for this function we can see the function is x less than 4, and if x is less than 4, means this is 0 1 2 3, so till here it will be true, and then for 4 5 6 7 it will be false. So for this function x is less than 4 and n is 3, we see that clearly we can see that it's a balanced function. And now we will use same code as it is to run this Deutsch-Jozsa algorithm. So you can see that we are not doing anything different here. Basically it's the same circuit which we used there, same code which we use for Deutsch algorithm. We are just increasing the number of qubit and updating the expression or function here. So let's run it, or yeah, we can run it now. So here in output we got 4 and function is balanced, and in output we got 4, means it is not 4 means it's not binary 4, it's this 4 0 0, this 4 1 0 0, so it's 1 0 0, and in 1 0 0 we know that all bits are not 0, that's why it's balanced function. Otherwise if all bits are 0, then it will become constant function. Let's see it in classic IDE to understand it better. So here this is our 3-bit input applied to Hadamard gate, and then this is minus state, Here phase kickback happens, and then we again apply 3 Hadamard transforms to get the output and measure it here. Now let's execute it. And after execution, we saw that it was 100, and in 100, since all bits are not 0, that's why it's a balanced function. And here we can see output as 4, and that's why we saw 4 in Jupyter Notebook. Now let's quickly modify our code. Let's make it 14 and run it. So now it will become a constant function, and in constant function all output will be 0. Here we got all output as all bit as 0 in the output, and if all bits are 0, then it will become a constant function. Let's see this circuit in VYDE. So this is the circuit, this one, and this time we see that we have these 3 input bits and we have this auxiliary qubit, but these 2 are extra, Q3 and Q4, which was not present in last case, and that's just because the number, the 13, which we are using here in our expression, the 14, we are using x less than 14. So that's why, because 14 can't be done using 3 qubits. That's why we have these 2 extra bits to handle that. And then I will not expand it. I will just expand this one. So again, we are applying Hadamard gate. Main thing is that after execution of this code, we should get output with all zeros. So if output is all 0, means it's a constant function. So this is what Deutsch and Deutsch algorithm is. If you want to see the mathematical calculation of this Deutsch algorithm, you can refer this guide from Classic. For some reason, mathematical part is showing as broken for me, but I remember when I saw it last time, it was working. Hopefully when you go to this page next time, it is working properly, or because page is still loading, that's why maybe it's not loading here. But yeah, here you can go and see the mathematics or mathematical calculation of Deutsch algorithm also. So we still had not seen the answer of question that why Deutsch algorithm is faster than classical algorithms. So we saw the circuits for both Deutsch and Deutsch algorithm, and one thing common in both is that for all our available inputs or for single input qubit, we apply the Hadamard gate initially, which take the states to superposition and thus making available all inputs for that function available because of superposition. Because if I take this q0 in superposition, then at this point it's both 0 and 1. Similarly, if there are 3 qubits, then because of equal superposition, all 8 inputs are available as input to this oracle, and depending on nature of function, it's valence or constant, phase kickback happens, and as a result we get plus or minus at this point, and thus final measurement we see 0 or 1. So in short, we can say that Deutsch algorithm is faster because it utilizes quantum superposition and quantum parallelism to query multiple inputs or all available inputs for that particular number of qubit at once, and that's why it's faster. Now at this point, you should stop the video and try to complete these tasks. I expect that you will complete these tasks, and if you stuck somewhere, then you will come back to video and continue. And I will continue with the solution of the tasks. So let's start with the task number 1. Here we have given number of qubits as 3, and we have to fill this expression such that this expression defines a constant function. So number of qubits is 3, means there will be 8 total input combinations like this from 0 0 0 to 1 1 1, and to get any function which is constant, either all outputs should be 0 or all outputs should be 1. So We know that inputs are from 0 to 7. If we write like this, x less than 8, this means that it's going to be true or 1 for all 8 inputs, and that's why it's constant. So you can guess any function, any expression which makes this function constant. This is not only one answer, there are infinite possibilities. Now after running this code, we should see 0 0 0. Let's execute in BYD also. Yeah, so here we got that this function is constant and output is 0. If we see in BYDE, so here we got 0 0 8 0 in the output, and we had seen that in Deutsch-Georgia algorithm, if all outputs are all bits in output are 0, then it's a constant function. Moving on to task number 2. So here in task 2, first question is that we have 4-bit input, and this is our function. We have to guess if this function is constant or balanced function, and then we have to write code to execute and synthesize and execute this circuit. So since n equals 4 means it's 4-bit input, there will be 2 to power 4, which is equals to 16 input combinations like this. And our function in our function we are checking that if input is divided by 2, is remainder equals to 0 or not. So these are all possible inputs, and this is corresponding output. So we can see that 8 are true here and 8 are false, means it's a balanced function. And to execute it, we can just use the same code which we used above. So let's just change the number of qubit and expression. So expression says equals 0. Now if I run it, we should see that it's a balanced function, and output should not be 0. So yeah, output is 1 and it's balanced function. In task 2, second question, given the function is either constant or balanced, then classically how many trials will it take to predict the nature of function for n equals 4? So in classical, in Deutsch-George algorithm, we saw that if we try to do it classically, then it takes 2 power n minus 1 plus 1 approaches, which will be equal to, for this case, it will become 9 times, means 2 power 4 minus 1 plus 1, which will become to 2 power 3, which is equals to 8 plus 1. So it will take 9 times classically to guess the answer if function is constant or not, but using Deutsch-Georgia, it will take only one shot. And coming to the third task, means third subtask inside second task, it says there are 4 qubit input, and this is the expression. We have to guess if this function is constant or not, constant or balanced. So here this expression is bitwise XOR, and if I go to, so here if we see, if input is 0 0 0, that is x is 0 0 0, and if we XOR it with 0 1 0 0, then we get 0 1 0 0, which is not equals to 0 0 0. Similarly for second case, this is not equals to this, and similarly for all these case and last case also, if we XOR 1 1 1 with 4, means 0 1 0 0, output is 1 0 1 1, which is not equal to 1 1 1 1. That's why for all cases output is false, means clearly it's a constant function. And in task 3, we have 1 bit input, and this is our function. We have to write the code and tell if this function is balanced or constant. So it's basically the same code. It's just for practice. You can refer this code and just update this expression and execute the circuit. It's as simple as that. So yeah, thanks.